Welcome to Chapter 8, Advanced Data Handling. By the end of this chapter, you'll understand the importance of sorting data, master the bubble, selection, and insertion sort algorithms, work effectively with multidimensional arrays, and handle records across multiple fields. Efficient data organization matters for three reasons. It optimizes performance. Proper organization reduces computation time and keeps applications responsive, especially at scale. It preserves data integrity and consistency. Structured storage ensures accuracy and prevents redundancy, minimizing processing errors. And it supports scalability. Well-organized systems are far easier to scale and adapt as datasets or queries grow more complex. This chapter covers three big topics. Sorting algorithms, like bubble sort and insertion sort, are fundamental for arranging data efficiently, enabling faster searches and analytics. Multidimensional arrays are ideal for representing complex datasets. Matrices, images, spatial data, and indexed files let you jump to specific data points within large files, dramatically improving retrieval speed compared to reading sequentially through everything. Sorting means organizing data into a specific sequence to improve clarity and usability. It makes datasets easier to analyze and interpret, simplifying tasks like identifying patterns, outliers, or trends. It's especially critical for finding the median, since sorting is exactly what puts the data in order, so you can locate that middle value in the first place. Ascending order arranges data smallest to largest, essential when you care about lower values or thresholds, like the minimum score in a dataset. Descending order arranges data largest to smallest, useful for ranking, like highest sales figures. Both orders are fundamental to calculating the median, since the data has to be in order, in either direction, to determine its central position. Sorting shows up constantly in the real world. In statistical analysis, it's a prerequisite for calculating the median, helping analysts pinpoint a dataset's center. In finance, sorting transactions by amount or date helps track trends like median expenses. And in healthcare, sorting patient data, age, blood pressure, helps identify median values critical for understanding broader population trends. The median is the value that splits a sorted dataset exactly in half. For an odd number of data points, it's simply the middle value in the sorted list. For an even number, it's the average of the two middle values. Sorting is indispensable here. Without it, there's no reliable way to know which value actually sits in the middle. And while either ascending or descending order gives you the same median, ascending is typically preferred for clarity and consistency. Finding the median follows two steps. First, sort the data so the middle value or values are actually in the right position. Second, check whether the dataset's length is odd or even. Odd means the median is the single middle value. Even means it's the average of the two middle values. The modulus operator makes that check trivial. Length mod 2 equals 0 means even, equals 1 means odd, and that single check drives the rest of the median finding logic. Here's the even case worked through. Dataset 12, 7, 9, 3 sorts to 3, 7, 9, 12. The two middle values are 7 and 9, and averaging them gives a median of 8. And here's the odd case. 5, 3, 8, 1, 7 sorts to 1, 3, 5, 7, 8. And since there's a single middle value 5, that's the median directly, no averaging needed. A single-dimensional array is a linear structure storing a sequence of elements in one row or column, also called a 1D array, list, or vector. They're a natural fit for representing a simple list, like student names or daily temperatures, whenever the relationships between elements aren't especially complex. The same array, declared in Java, C++, and Python, looks almost identical across all three, just curly braces or square brackets holding a sequence of values. Multi-dimensional arrays extend that same idea into multiple dimensions, 2D for tables or matrices, 3D and beyond for even more complex structures like grids, images, or 3D models. A 2D array is perfect for representing a table with rows and columns, like student scores across several subjects, or spatial data like pixel values in an image. Java, C++, and Python each declare a 2D array as rows of rows, the same underlying structure, just different syntax. Here's looping through a one-dimensional array as actual code in C++, Java, and Python. Each version calculates the array's size, then loops through printing every element alongside its index. Identical logic, producing identical output across all three languages. Here's looping through a two-dimensional array in C++, nested for loops, an outer loop for rows, and an inner loop for columns, printing each element by its row and column index. The output confirms every value gets visited exactly once, in row-by-row order. Here's that same 2D array loop in Java, the exact same nested loop structure, outer loop for rows, and inner loop for columns, producing identical output to the C++ version, just using numbers.length-style array access instead of C++ syntax. And here's the same 2D loop one more time in Python, nested for loops over range, rows, and range cols, indexing into a list of lists to print each element by row and column. Same structure, same output as both the C++ and Java versions. Swapping means exchanging the values held by two variables or array elements, a technique you'll use constantly in sorting algorithms like bubble sort. In most languages, that requires a temporary variable to hold one value during the exchange. Temp gets A's value, A gets B's value, B gets temp's value. Python is the exception. Its tuple assignment, A, B equals B, A, swaps both values directly in one line. No temporary variable needed at all. Bubble sort repeatedly steps through a list, comparing adjacent elements and swapping them if they're in the wrong order. It runs in O(n) squared time, making it inefficient for large datasets. It's best suited for teaching the concept or very small lists. It's typically implemented with nested loops and includes a useful optimization. If an entire pass completes with no swaps at all, the array is already sorted, and the algorithm can stop early. Here's bubble sort traced through step by step on 5, 1, 4, 2, 8. Each pass compares adjacent pairs left to right, swapping whenever the left value is bigger. After the first pass, the largest value has bubbled, all the way to the end. Each subsequent pass repeats this on a slightly shorter unsorted portion, since the end of the array is already correctly placed. 4 passes total fully sorts this 5-element array. Here's bubble sort as actual C++ code, sorting 64, 34, 25, 12, 22, 11, 90. The outer loop controls each pass, the inner loop compares and swaps adjacent elements, and a swapped flag tracks whether any swap happened in that pass. If not, the array is already sorted, and the loop breaks early rather than running all the remaining passes for nothing. Here's that same bubble sort logic in Java. Identical structure, outer loop for passes, inner loop comparing and swapping adjacent elements, and the same swapped flag enabling an early exit the moment a full pass completes with 0 swaps. And here's bubble sort one more time in Python. The same nested loop structure, using Python's tuple swap syntax instead of a temporary variable, with the same swapped flag driving an early break. Identical logic and identical output to the C++ and Java versions. Selection sort divides the array into a sorted portion at the front and an unsorted portion at the back, repeatedly finding the smallest element in the unsorted portion and moving it to the end of the sorted one. Like bubble sort, it runs in O(n) squared time, but it performs noticeably fewer swaps, which can make it faster in practice in certain situations. It's implemented with nested loops. The inner loop searches for the minimum, and the sorted portion grows by 1 element each pass. Here's selection sort traced through on 64, 25, 12, 22, 11. Each pass scans the entire unsorted portion for its smallest value, then swaps that value into the front of the unsorted section, growing the sorted portion by 1 element every time. 5 passes later, every element has been placed, and the array is fully sorted. Here's selection sort as actual C++ code, sorting 64, 34, 25, 12, 22, 11, 90. The outer loop advances through the array. The inner loop scans ahead to find the index of the smallest remaining value, and a single swap places that minimum at the front of the unsorted portion. Notice the swap only happens if a smaller element was actually found, skipping unnecessary work. Here's that same selection sort logic in Java. Identical 2-loop structure. Outer loop advancing through the array, inner loop tracking the index of the smallest remaining value, with 1 swap per pass placing it correctly. And here's selection sort in Python. The same nested loop pattern, using Python's tuple swap syntax for the single swap per pass. Same logic, same result, as both the C++ and Java versions. Insertion sort builds a sorted portion incrementally from the left, inserting each new unsorted element directly into its correct position within that sorted portion. It runs in O(n) squared time in the worst and average case, but drops to O(n) if the array is already sorted, and it sorts in place using O(1), extra space. Rather than swapping, it shifts elements to make room for the value being inserted. It's especially efficient for small or partially sorted datasets, and it's stable, preserving the relative order of equal elements. Here's insertion sort traced through on 5, 2, 4, 6, 1, 3. Starting with just 5 as a 1-element sorted portion, each pass takes the next unsorted value and inserts it into its correct spot among the already sorted elements, shifting others over as needed. 5 passes later, every element has been inserted into place, and the array is fully sorted. Here's insertion sort as actual C++ code, sorting 64, 34, 25, 12, 22, 11, 90. Starting from the second element, each one gets stored as the key, and a while loop shifts every larger element in the sorted portion 1 spot to the right until it finds the key's correct position. Notice this shifts elements rather than swapping pairs, which is what sets insertion sort apart from bubble and selection sort. Here's that same insertion sort logic in Java. Identical key and shift approach. Store the current element as key. Shift larger sorted elements rightward with a while loop. then drop the key into its correct spot once the shifting stops. And here's insertion sort in Python, the same key and shift pattern, using a while loop to shift larger elements rightward before placing the key identical logic and output to both the C++ and Java versions. Parallel arrays get sorted together by designating one as the key array, the one whose order you actually care about, and rearranging every other array to match. If names and ages are parallel arrays, and you want people sorted by age, ages is your key array. Sort it first, then rearrange names using that exact same new order, so each name still lines up with its correct age. 3 steps. Identify the key array, sort it, then rearrange every other array to match. No new assignment this time. Just make sure your Canvas assignments are complete, and bring yourself to class ready to learn. We'll be building directly on sorting, multidimensional arrays, and the concepts covered throughout this chapter.